On the first Sunday of every month at 11 theater, we are live from a lab in India. So in this world today where everything seems entangled from wars and LPG prices and everything seems mixed up, going down to the very basic level, it's very fun to discuss entanglement, but at a quantum level. And to tell us about it, we have Kiran, who is a PhD student in PIFR in the Department of Nuclear and Atomic Physics, where she works on in a lab that deals with the overall area of quantum optics. So optics, but looking at it, the quantum properties of light. And part of this is this phenomenon of entanglement that she will try to tell us. However, let me introduce her. Kiran is from Haryana. She grew up in Pani, did her bachelor's there, moved to Delhi for her master's, did her master's at IIT Delhi, and then came to PIFR for her PhD, and where she is right now. And she's going to be telling us about this. So all over to you. Now remember that your mic is only for the online audience. Here there is no mic, so make sure that people can hear you. And if you don't understand us, please stop and ask us. And just so that I tell everybody, 2 weeks from now we will have a fifth Sunday where we will be looking at the lab that makes something called the Motional chambers, or these are resistive state chambers, which are detectors for neutrinos. We will be in a lab that does this. Show you the lab, go to the lab online, and you can watch it on YouTube. After that, the first day of April, we're going to be at Prithvi with a topic in chemistry called I spy molecule, and we're going to have Sir Ankara Datta tell us about how they detect a particular molecule having some particular element inside cells. So that's going to happen at 3 on the first Sunday of April. But before that, there is a 5th Sunday of March. We will be at the RPC lab in PI. Okay, so with that, it's all yours. Now you can share screen.
Yeah.
And,
Let us scroll back. Yeah. Are we good? Hi, can you all hear me? Yeah, good. So hello, I'm going to talk about quantum entanglement in which I work in day-to-day life. So I'm going to tell you the story of quantum entanglement and how it started. Uh, so it all started. I'm so sorry. Blue filter. Stop sharing screen. Can you stop us?
you can
I'll stop here. Camera status here. I'll stop it again. Mhm. It's not swapped. It's yeah, very good. Yeah, we sorry. Uh, so it all started 100 years back when we call 1925 as the birth year of quantum. And last year, the year 2025 was celebrated as International Year of Quantum Science and Technology. There are a lot of scientists behind the discovery of quantum mechanics, and a few of the contributors are here. Um, and well, when we talk about quantum mechanics, what we talk about, what is quantum mechanics? So it's the science, it's the physics that defines the how the very teeny tiny particles behave, such as photons, atoms, or subatomic particles behave. And it's not very intuitive because the particles we see around us are usually centimeter, meters big, and whatever our intuition is developed from the particle we see around us in day-to-day life. While on the other hand, when we go to these subatomic particles, they start behaving very differently. So let's understand what is the scale we are talking about. Uh, Here it is. So let's say we have a cat, so which is almost this big, let's say 30 centimeter. And then we go to cell, which is trillions times smaller than that. Trillion is like 10 to the 9. And then we go again trillion times smaller, and then we go to uh, so then we go to like a nanometer scale, and that's where molecules come, and that's the scale we are talking about, the quantum scale. And so when we go to that scale, what happens is we start seeing it discretely. We start seeing the atoms. Uh, yeah, yes, sir. So while on the classical scale, we can see like we can say that the water is 1 liter. There's 1 liter of water, and then we can also say there is 1.5 liter of water or 1.15 ml of water. So we can talk in terms of continuous numbers. But when we go to these quantum scales, there is a smallest unit which we call quanta, and we cannot break it down further. For example, we can say one atom, two atom, but there's no such thing as 2.5 atom. And that's the same for number of particles, energy, and momenta. There's smallest scale of momenta, and then energy as well. And everything seems discretized, and that's the scale we are talking about here. Uh, Going to, if we go to such scales, the particles start behaving very differently from what we are used to seeing. And one of the behavior which we see in quantum particles is wave particle duality. So every particle acts as a wave as well as a particle, and it depends on how we observe it. So, what do you understand from a wave? What is a wave? So, it's this waves in the ocean, right? And what is one of the characteristic of the waves? It's wavelength. Do you understand wavelength? Yeah. So wavelength, which we usually represent by this weight character lambda, and the particle is usually represented by its position in the 3D space x and corresponding momenta in the 3D space p. So now every particle, every quantum particle has both the characteristics, and when we have p, we can find out the corresponding lambda for that, which is given by this formula p is equal to h by lambda. So now we have a quantum particle, which is also a wave and also a particle at the same time. Now, what happens is understanding it further is a little tricky. So let's see what happens. Let's say we are trying to create waves in a rope. So we are holding a rope and we are creating waves, right? So can you define wavelength for this? So we have this maxima, then again minima, maxima. And we can define a wavelength by looking at it like minima to minima distance or maxima to maxima distance, right? So that's the wavelength. But can you define where the wave is? What is the position of the waves? The wave is spread throughout the rope, right? So we don't know its position. So even though we know the lambda, and because we know the lambda, we know the momentum, but we don't know the position. Now, let's look at the other case. We give the rope a simple jerk, and that will create this small pulse. And in this case, we can define the position, right? This is the position of the wave. But cannot define the wavelength because there's no two maximas or no two minimas to define the wavelength. So in this case, we can define the position, but we cannot define lambda, and therefore we cannot define the momentum. So that gives us second feature of quantum mechanics, which is we cannot define position and momentum of a quantum particle precisely with arbitrary precision at the same time. You understand? Yeah, right. So that's the uncertainty principle. So the uncertainty in position and the product of uncertainty in position and the momentum will always be greater than a particular number, and that is h cut by 2. If we try to make this number smaller, this will increase, but this will always be greater than by 2. So this can be understood like this, and this is called Heisenberg uncertainty. So let's say we have quantum particles passing through a slit. We have a slit blocking the particles which are going in this direction, and they are falling in the on a screen which is kept in the far field. So the screen, where the particle is passing through in this slit is defining its position. But here, where it will hit at the screen will be defined by the direction in which the particles are going. So let's say if the particles are going in this direction, it will hit over here. So on the screen, the position will be defined by its direction, that is its momentum. So in this case, our delta x is this much, and the delta p is this much. Uh, but now let's see if we are trying to decrease the delta x. How can we decrease the delta x? By selecting only those particles which are passing through very small regions. So we can narrow this slit down and try to decrease delta x. But what will happen in that case is the particles will start spreading in this direction, and the delta p will increase, so that the uncertainty principle is preserved. This we can understand in the sense that if we turn on a tap of water, the water flows like this. But when we try to block it with the hand, it starts flowing in every direction. So that's the type of thing happens here. So that's the uncertainty principle, and which says that we cannot measure position and momentum at the same time with arbitrary precision. And this applies to a lot of other set of variables, which we'll not discuss about today. Let's just stick to position and momentum. But yeah, there are a lot of complementary variables that shows these properties. Now, the next thing about quantum mechanics is randomness. What do we understand from randomness? We can see randomness all around us. Like, let's say we flip a coin, it can give us head or tail, right? That's random. And in the same sense, let's say we have a box which has two balls, which is an orange ball and a blue ball, and we can randomly pick one of them. And let's say we took out one of them, but we have not looked at it. Like we took out one ball and we're not looking at it what it is. We take it very very far away from here, and then we look at it, and turns out it's orange. So, what do you think? Like the ball is or was orange to start with. When we took out, was it orange, or did it turn orange when we took like we looked at it? So, was it orange here, or what did it turn orange here? Starting से ही orange होगा. So yeah, that's right. So that's the thing about the particles we observe in day-to-day life. They have well-defined properties. Starting say like the ball will be orange from very start. So the randomness in our day-to-day life comes from ignorance. Because we don't know, we didn't look at the particles, like we jumbled it up, and we were not able to track where the particles were going. That's why it's random. If we would have tracked the particle, then it would not have been random. We would have determined it that the ball we picked is orange or blue. So that's the randomness we observe in our day-to-day life, and the randomness in our life is because of our ignorance, because we don't know how the things are moving. So if we, for example, while flipping a coin, if we know exact force with which we are flipping the coin, we can know whether it will be head or tail. So that's why there is randomness. And about the measurement, so we performed a measurement here. We looked at it, which is a measurement. So in classical world, what happens is measurement reveals the fact. The fact was already here. So when we took it out, it was already orange. But when we measured it, it revealed the fact that it is orange. But the fact was already here. Well, on the other hand, when we talk about quantum particles, which are extremely small particles, if we do the same experiment with quantum particles, what happens is, let's say we take out one of the particles and we take it very very far away, and then we measure it. In this case, uh, the measurement because the ball turns orange because of the measurement. So up to here, the particle was orange and blue at the same time. But when we measure it, it turns into either orange or blue randomly. And quantum mechanics says that it is completely random, and it's not because we don't know about it. It's not this randomness is not because of our ignorance. It's just completely random, and we don't know which particle is going to turn orange or which particle is going to turn blue up to the end. So that is one more thing about quantum mechanics. And in this case, the measurement is an act of creation. The measurement is what is creating the fact that the measurement turned this particle orange, basically. So that was about quantum mechanics. Now this all happened century ago, and when it was formalized, uh, and again, yeah, the results are random. So when it was formalized, Einstein was not happy about it. He said the physical properties should be well defined. It's not like a particle can be orange and blue at the same time. He said, like, do you really believe the moon is not there when you are not looking at it? And he said God does not play dice, so the results cannot be random, and measurement is not what creates the results should be there. The physical entities of a particle should be there whether or not we are looking at it. So that was about him, and then he thought a lot and he designed a paradox. So this is going to be a little challenging part. So please ask me questions if you don't understand it. So he said, let's take, okay, for a while, I'll assume that quantum mechanics is right. Whatever you said, the uncertainty principle, the wave particle duality, the random results, everything is right. And the measurement is act of creation is also right. And I'll start with a quantum state, which is allowed by quantum mechanics. I'll take two particles such that x1 is equal to x2, so such that their positions are same and momentum are equal and opposite. Basically, they are traveling in the opposite direction. Uh, and the such states are allowed by quantum mechanics. So he started with such state, and he said, I'll separate them. I'll take one of the particles on one side and other on the other side, and I separate it by a lot of distance. Like I take one of them to the sun and the other one to the moon, so to the earth, and then I perform measurement. So I measure x of one of the particles and p of the other particle. So when I measure position of one particle, uh, I instantly know the position of the other particle, right? Because x1 is equal to x2, right? And so when I measure x of particle one, I know position x of particle two. But now I can also measure p of particle one, particle two, right? Then which means that I know position and momentum of the second particle, both of them. But uncertainty principle says that you cannot measure both at the same time, right? Then you can also say because we measured position of one particle, the other particle knew that the position has been measured. But the catch here is that what is the distance between the sun and the earth? How much time that sunlight takes to reach from sun to earth? Yeah, yeah, that's right. So it's around 500 seconds. So if you perform the two measurements within 500 seconds, there's no way the particle 2 will get to know that the measurement 1 has been performed. So we will know position as well as momentum of the other particle, which is against the Heisenberg uncertainty principle, right? So it said either the Heisenberg uncertainty principle is not able to stand, or you have to say that the results are not random. You have to say that the position and momentum, everything was defined when we started. Because if it was defined here, then there's no way the information can travel faster than speed of light, and this, which means that we can measure both position and momentum. So that stood for a while, and it was given in 1935. And from this, they said that, well, there's something wrong with quantum mechanics, and quantum mechanics is incomplete. So these states, because these three scientists, Einstein, Podolsky, and Rosen, gave these states. These states were known as EPR states, and these were the states which were later called entangled states. So to understand this situation, scientists came with a lot of ideas, and one of them was hidden variables. So they said, yeah, sorry, we'll come to that. Yeah. So scientists came up like that. Scientists thought that what they said, like the measurement is not random and everything is defined over here when the particles were created. They said maybe something is hidden and we don't know about it, and that gave us hidden variables. And what hidden variable says is, let's say we take out one of the particles, one of the quantum particles, which had some variables A, B, which had some values, but these values we are not able to measure. That is, they are hidden from us. But these are the variables which defines to starts with whether the ball is going to turn orange or uh, blue when we measure it. So it doesn't matter when how far we take it, but the results were defined here only when it was created, and uh, that gives the results. These variables are what measures the results. So it was same as somewhat like classical, that because it is coming from our ignorance. So because we don't know the value of these variables, and that's what defines. They said that's what defines what are going to be the results. That was the hidden variable theory, and they said the only difference in quantum mechanics is there's no way we can measure it, and that was hidden variable. But how do we prove that the hidden variable theory is correct or quantum mechanics is correct? Because the thing is, we cannot measure it twice. Because if we measure it here, which that means that the according to quantum mechanics, the state is already changed because measurement changes everything. So we cannot measure twice to verify it. So how do we verify it? And what do you think is correct? Is the quantum mechanics complete or the hidden variable theory is correct? So, how many of you believe that quantum mechanics is complete? Yeah, raise your hand. No. How do you think the hidden variable theory is right? So there are two parts. Either the quantum mechanics is complete or hidden variable theory is correct. I, so you think hidden variable theory is correct? So how many of you think that hidden variable theory is correct? Raise your hand. No. Quantum mechanics? Okay. I think there's no opinion right now. So there was a confusion whether quantum mechanics is complete, whether the results we are seeing are completely random and are determined by the measurement, or they are predetermined by some variables which are hidden. So to measure this, scientist called John Bell suggested this in 1964, and he said that we take these EPR states, and what we do is what they suggested. Uh, he assumed that there are random variables, there are hidden variables, and then he took this variable very far away, and he randomly measured position or momentum of first particle, and the same he did for second particle. And he said if you can create such states again and again, make a lot of copies of it, then and perform the same measurement for every set of variables, then there will be this uncertainty. And if you can violate this uncertainty, then we will know what is correct. So he just basically proposed an experiment, which will, if you can perform this experiment, you'll know what is right and what is not. And such inequality can be performed for, I told you, like the uncertainty principle is there for different set of variables. So it can be performed for any of those set of variables. So to perform this experiment, so well, this was proposed in 1964, a long back. Uh, but the first experiment, the first Bell test, was performed in 1972, where they did it with uh, photons, and uh, they did similar type of experiment to find whether hidden variable is correct or quantum mechanics is complete. But scientists said that you said like take one particle to the sun and keep one on the moon. So maybe the part, because you're doing this experiment in the lab only, maybe the particles are talking to each other, and that's why the results you are getting may not be right. So that's what we called loophole. And people kept on finding loopholes in the experiment uh, until 2015, where first time, yeah, sure. So in the experimental details, what they did was they created such states here, and then they passed one particles through this side and the other through this side, and they performed the measurement. But everything was happening in on the lab scale, and they found out that the quantum mechanics is complete. There are no hidden variables to start with. But again, like since we said like there were loopholes, and to uh, understand the loopholes. We try to eliminate those loopholes one by one. Yeah. So the okay. So since I told you that there are position and momentum measurement we can do, but such type of measurement can be done on different particles and different set of variables. So the degree of freedom used in this experiment was actually polarization. So they use polarization degree of freedom, and we can control or measure polarization by different optics components in the optics lab. So they have used the polarizer, which are used to measure different polarization. And then these are all electronics they use to understand when the photon arrived. And if the two photons are arriving at the same time, those are the ones which are entangled, and so on. And there was a setup, and they created those from atoms, the photons from the atoms. And then, uh, uh, sorry. Yeah, yeah, lower energy. Yeah, yeah, hmm. Yes, yeah. Yeah. So we detect, So what we do is like we need two set of variables, which is x and p, position and momentum. In this case, it is replaced by polarization, and the measurements are we know that when light travels in this direction, it can have polarization, and polarization is defined by the direction of oscillation of the EM wave. So the polarization can be, if you look at it, it can be anything in this plane, in the plane perpendicular to the propagation direction of the light. So it can have any polarization. So in this case, the X and P are replaced by polarization. So one will be replaced by horizontal polarization, horizontal or vertical. So a photon can either be have this polarization or this polarization if light is traveling in this direction. And the other measurement is 45-degree polarization. So, and the way we measure polarization is by rotating these polarizers. So the polarizers are the component which only allow a particular polarization of light to pass through. So if we put only allow vertical polarization to pass through, then it will only allow those photons. And if we rotate it, the polarization can, then we can allow 45-degree or 90-degree or whatever, however we align the polarizer to be, right? So we adjust. So the way we said, like we randomly measure position or momentum, which will be here equivalent to, we randomly measure whether it is 0 90 or 45 minus 45. That is by changing the polarizer, and that the polarizer setting basically. So because the experiment was performed in the lab, then, and we can, there's a rate at which we can rotate the polarizer, which means that people said maybe this setting was known by this photon and so on. So if the photon could talk, then in principle the information can leak, and that's not a foolproof way of saying that the experiment was successful. So that was what they called loophole, and that was, yes, yes, yeah, 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 yeah. So like people went on doing experiments and went on refining the experiment, but uh, there were more and more loopholes, and finally in 2015 it was first time when someone performed Bell experiment demonstration, which was separated by 1.3 kilometer. Well, it turns out we don't actually need to take a particle to sun. We just need a distance so that our detectors are faster than the separation. Uh, and that's what they did. And this is how they did. They generated photons and then they sent it very far away and measured it there. And they made sure that the separation is so much that the particles they cannot talk. The distance is uh, more than light-like distance, which basically means if the measurement is fast enough that there's no way, there has to be a communication that has to be faster than speed of light, which is not possible. And turns out quantum mechanics won. So how can it happen? But the question is, how can it happen? Because this basically means that there's something happening more than speed of light, right? So that's what we call spooky action at a distance. Uh, what a general theory of relativity says that information about distant objects can arrive no faster than speed of light. And here it turns out that if you are measuring position of one particle, the second particle instantly knows that the position is getting measured. And the state of the second particle also changes, because if it's not changing, that it means that the Heisenberg uncertainty principle is getting violated, which is not possible. So the fact is, yes, indeed it is happening that when we measure the first particle, instantly uh, the state of the second particle is also being measured, and the state changes. But we are not also violating the causality here, because the results here are random. Uh, if we measure position, it can be anywhere throughout the beam. And that's what quantum mechanics said, right? The results will be random. The ball can be orange or blue at with equal probability, somewhat. So because the results are random, we cannot actually control the result. We cannot say, okay, I'll turn this particle orange so that the particle turns blue, and I can just say the person handling the other particle, if it turns blue, then you do this task. Otherwise, you don't do this task. If you could actually control that, then they can be useful transfer of useful information. But because the results are random, we cannot actually transfer any information, and that's why it doesn't violate the causality, because there is no even though it is instant, information transfer is not happening here. And that was the thing. So fast forward to today. Today we are in second quantum revolution, where we know how quantum mechanics behaves and what are entangled states, and we are no longer wondering about that. But we are converting it into technologies which might be affecting us in a few years. So some of the quantum technologies are quantum computing, quantum sensing, and quantum communication. So we can use the entangled state for all these things. We can use it for computing, which can make our computer much faster, and measurements, which can allow us to measure the more precisely than what is allowed by classical systems, and quantum communication, which can allow us to communicate with someone else more securely. You can see when you look at your WhatsApp, it usually shows the message are encrypted. So today, most of the technology is encrypted because of what we call classical encryption, which works on the principle that the computation is so hard that no one can crack it. So, but once we will have more powerful computer, maybe someday we'll be able to. Yeah. So John Bell, no, he's a complete. So John Graham Bell is a. So John Bell was a quantum physicist, and yeah, so he's different from Alexander Bell. Quantum information is using quantum mechanics to uh, okay, so quantum information is basically using quantum mechanics and using deriving some things which can be useful for us. Study of the basically study of quantum mechanics. Yeah. Do we have any more questions? So yeah. So quantum mechanics is when we talk about particles whose nature cannot be understood. Yeah. So quantum mechanics is uh, so quantum in this case is we are talking about the states or the particles which cannot be defined by the classical behavior, and classical laws like Newton's law and everything. And when we go to the scale, when everything the energy levels are discrete, the momenta and the particles are also discrete. So we are using those properties, the quantum properties, in the application property. Yeah. Yeah, sure.
I can make measurements that are
Yeah. Yeah. So we are actually applying the laws of quantum mechanics to applications. And what we work in our lab is on some part of quantum communication. So we work with photons, which are very low level of light. We are not going to the scales which are very small. Rather, we are going to very low level of light. We can deal with individual quanta of light, which are photons. So we most of our experiments are performed in very low light. Yes. So usually the way we define it is uh, the if the our detector is fast enough to distinguish between every photon it gets, then like our detectors are the determining thing. So let's say if my detector can distinguish 10 to the 6 photons per second. So if I'm going lower than that, then I can exactly tell when a photon is coming and where it is coming, and that's what determines. Uh, no, it's actually the number of photons for a detector, but we study the features which are also something which are not determined by classes. So we work with that, and we generate entangled photons in our lab using a non-linear uh, crystal, which shows this phenomena called spontaneous parameter down conversion. Let's not go into terms. So what it basically does it, when we shine light onto it. So let's say we have a sheet of glass, and we are shining blue light on it. What will happen? The blue light will pass through, right? And if you're shining red light, then red light will pass through. So this is a specific kind of crystal which actually looks like a glass, But what happens is when we use shine blue light, some of the blue light will be converted into red light. And what actually happens is because, as you said, wavelength, uh, because the wavelength of the red is double, and the energy is hc by lambda. It's inversely proportional to wavelength. So according to conservation of energy, uh, one blue light photons can actually create two red light photons. So that's what happens here. When we pass it through this, the one blue light photons break down into two photons, and because it is getting created from a single photon, according to conservation of momentum, they will propagate in the direction so that the momentum is conserved. But again, because it's created from a single photon, they will be created at the same point. So they will be correlated in position and anti-correlated in momentum. So K1 is equal to minus K2. Do you remember this state? Have we looked at it before? So these are the EPR states which were there in the 1927 paper. Yeah. It's not quite scattering. It is a non-linear process. So do you know, like, there are atoms inside, and there are atomic levels and molecular levels and so on. So the molecules absorb energy, absorb photons, and go to the higher level, and then it comes down according to the atomic level scheme. Yeah. So, but there's something different here. So when we talk about this level, these are real atomic levels. But in this case, we what we use are virtual levels, which are a little different from the real levels. Yeah. No, no, the atomic levels, the levels are energy levels are virtual. Yeah, so that happens because the photons actually break down, and what we see in the position plane is that they are correlated, and in the momentum plane they are anti-correlated. And these are the EPR states, and we can use them for a lot of things. What we do is we can use it for quantum communication or quantum key distribution. So we can say if the photon is coming over here, then we can call it 1, 2, 3, and we can assign an alphabet corresponding to each position. And we are trying to make a scheme so that we can optimize uh, the efficiency of it. And further, we understand that if we are using it for practical applications, there are going to be problems with that. We have a lot of noise coming from different places, and how to deal with that noise. How is the noise going to affect these correlations? And we are having more fundamental studies like phase entanglement. So that's it. Thanks a lot. This is my lab. Uh, Uh, this is no more STIFR, and I would like to thank Chai and Wai for giving me this opportunity to present here. And yeah, thanks. Yeah, we can take more questions. Yeah, sure. Yes, I don't understand it. Yeah. I don't understand it. So I'll try to answer this question from my understanding. Yeah, yeah. If anyone has questions, please feel free. Yeah, that's it. So if a particle is passing through something and it's remembering what has already been happened, then yeah. Uh, as per my knowledge, no, because a quantum particle can hold only a limited amount of information, and if it is holding that much amount of information, uh, I don't think it's possible. So I say, as per my understanding, I mean, the world keeps changing. Coherence of two entangled particles. Well, yeah, that's okay. I'll just tell the answer, assuming that the person knows a lot of about coherence. So when we talk about photons, and let's say we are talking about polarization, I'll start with polarization. Uh, for the photons to be polarization entangled, uh, first thing they need to have is the polarization of one of the photons will not be well defined because it can be H or V. But once we define horizontal or vertical, but once we find out that one of the particle polarization is horizontal, then other ones turns out to be vertical. But we need to start with the uncertainty that the first particle can have horizontal or vertical, and that's where when we talk about coherence, uh, and we look at one particle, then there will be it can be horizontal or vertical and or incoherently. So the coherence in one photon space will be lost and will be transferred to the two photon states where they are entangled. And same can be understood in terms of polarization position momentum entangled. So what happens is for these correlations to exist, the beam is this big and the photon can be found anywhere throughout the beam. But once we find out that one photon is here, the other one will also be there. And it can happen everywhere across the beam. But when we define spatial coherence, we say that the photons which are here in this part of the beam have phase correlation with other part of the beam. So that coherent is not present in the single photon space. So if we put a double slit, we will not be able to see fringes in this case in the intensity. So yeah, it's transferred to the two photon space. In case of decoherence, oh, oh, I think that was a question. I understand that now. So uh, for all of the macroscopic objects we observe around us, uh, the individual atoms interact with a lot of other atoms which are present around them, and that leads to transfer of energy. And they are not because they are not isolated enough, and that's what caused the decoherence of the state. So the state which we started with will no longer be that state because it interacted with it. So the decoherence that will cause the yeah. In the case of decoherence, it will not be yeah if it interacts with surrounding yeah. Yeah. Hmm. Yeah, we'll take that. Yeah, can I remove the mic? Yeah, thank you so much. Yeah.